So how do massive neutrinos become observationally interesting in cosmology? Now, first of all, there is this, as there is a cosmic microwave background, there's a cosmic neutrino background, and it's formed in a kind of similar way. So the cosmic microwave background forms when neutral hydrogen becomes the thing in the universe. When it cools enough that hydrogen can form, it spits out all this light, and that light is there and doesn't really interact much until we detect it. Interacts a little once reionization happens, which I mentioned earlier in the stream. The cosmic neutrino background is formed earlier in the early universe, when the universe cools enough that there isn't enough energy to be constantly creating new neutrinos. Then the cosmic neutrino background is formed. Now this, in a massless neutrino paradigm, is just there as massless radiation. Its effect on the expansion is exactly the same as radiation would be, and one can measure how much excess radiation there is beyond what we see as visible light, and this is parameterized normally by the effective number of neutrinos, and does turn out to be about 3. The cosmological measurements of this exist, and the value is consistent with 3, and we expect 3 neutrinos, 1 electron, 1 mu, and 1 tau. So we know that this cosmic neutrino background is there, and we know that it's probably around about 3 neutrinos. If these neutrinos have mass, then eventually the universe cools so much that they stop acting like this very high energy radiation and start acting more like dark matter. And in fact, there's like a 2 or 3 year window, and I think in the 1980s, I wasn't around back then, or at least if I was around, I was not talking about cosmology. I was 1 or 2 years old, where they were completely convinced, because dark matter had started to become obviously needed, and neutrino mass had started to become obviously needed, and people were like, well, we've solved the problem. Dark matter is neutrinos. And neutrinos are dark matter, and they are weakly interacting, so they don't interact with light enough to not be dark matter. The problem is that they're too light, and they would have too much energy to cluster the way dark matter clusters, and they wouldn't have enough mass in total. When you say this is how many neutrinos there must exist, this is how much mass they have, therefore this is the total amount of mass in the universe, you just don't even get close to the total amount of mass that we see. But they do have mass, and so therefore they will be some fraction of the dark matter. And this will mean that the way dark matter clusters will be influenced by that. So here's the dominant effect, or at least what I think is the dominant effect. While the universe is evolving and sort of structures are forming, while things are falling into gravitational wells, the cold dark matter will fall into whatever gravitational well it is closest to. If it's here and there's slightly more mass here, this dark matter will fall into this mass, because it starts off without any motion. It's just sitting there, and then this is attracting it, it falls into it. With neutrinos, because they start off very, very rapidly moving, unless this gravitational well is so strong, like it's so much mass here, they won't fall into it. They'll move, they'll gain a bit of energy as they fall in, but then they'll have enough energy to get out. A bit like if I push a ball down a hill, if I push it hard enough, it'll get back up over the other hill. But if it starts stationary, it'll always fall into the valley. So what this means is that neutrinos will aid clustering on very large distance scales, because the total amount of mass inside a well this big is much bigger than the total amount of mass inside a well this big. So a neutrino will fall into a very large distance scale well, because it just can't get back out the other end. Like it might fall to here, and then as it's trying to climb out, it just doesn't quite make it. Whereas if the well was this big, it's trying to climb out, it definitely makes it. And so neutrinos aid in clustering on big distance scales, but don't aid in small distance scales. And that means that if you say, give neutrinos some mass, but keep the total amount of dark matter consistent, then you actually are saying there's slightly less of the other types of dark matter, the cold dark matter. And so therefore, what you see, coming back to one of these correlation functions, if you don't know what a correlation function is, I recommend checking out the YouTube channel, where there will be me talking about correlation functions for a few minutes. But a correlation function is telling you about how things cluster on certain distances. So what you might already be able to kind of predict here is that if you have neutrinos with mass, then the small distance scale correlation function is decreased, and the large distance scale one is increased. So you would see that as evidence of neutrino mass. In future experiments that are measuring the locations of galaxies on the sky and how much they've been lensed, this will be an observation that will be seen. Also, the cosmic microwave background is itself being lensed by local structures. As the light from the cosmic microwave background travels to little Earth here, if there's a galaxy here in the way, then the light gets lensed. And this is actually something that is one of the leading sources of information coming from the cosmic microwave background now, is how much it's getting lensed. So it also is sensitive to this effect, and there will be future better cosmic microwave background measurements. And yeah, and this is something that projections of how well this effect will be measured say that we should be able to see